Section 2.5, Graphing Linear Inequalities. Now, up until now, Unit 2 has been all about systems of equations, so we'd always have two equations happening at the same time. For this section, though, we're only going to be doing one at a time, and that's because we need to first see how a linear inequality works. Not a linear equation, these are the linear inequalities. So what is a linear inequality, or any inequality? It's a mathematical statement using less than, greater than, less than or equal to, or greater than or equal to. So what it's saying is one amount is going to be less than another amount, or one amount is going to be greater than or equal to another amount. So there's not necessarily just one thing that works, one value. If I said something like I wanted an amount x that's greater than 4, okay, well, there's a lot of things greater than 4. I could have x is 5, I could have x is 7, I could have x is 720. Okay, there's a lot of things bigger than 4. Okay, it just excludes some things, like anything that's exactly 4 or less than 4. Those are, it's a certain range that we can't have. Okay, so examples of what a linear inequality looks like would be something like if we can get y is less than or equal to 3x plus 2. Okay, notice how it still kind of has the y equals mx plus b form. Okay, in this case our slope, our b, is our 3. The y-intercept is this 2 over here. And then we still have y and x in their place. So it still looks like one of our lines, or one of the equations for a line. It just, instead of having the equals to, it has this inequality symbol. So what it's saying is we're going to be on that line, but we want everything less than that line or below that line. So that's how these inequalities are going to look. Another example would be, again, sometimes we're not given things as a y equals mx plus b form. This is a standard form, remember, ax plus by equals c. Well, this is a standard form linear equation, but it's not an equation. Again, it has that inequality symbol, so something greater than. Okay, and just like how we can take one of our standard form equations and change it into y equals mx plus b, we can do the same with these inequalities. I'll show you how that looks here. Okay, so again, this video is going to be all about working with the inequalities. Okay, so a concept map here, steps for graphing linear inequalities. Step number 1 is always to arrange the inequality so that we get it in slope-intercept form. Okay, in a lot of problems this will already be done for you. We'll already have y is greater than, or y is less than, or whatever it is, mx plus b form. Okay, but remember, this y equals mx plus b form is the one we're looking for. The only difference is it's not going to be equal to, it's going to be greater than, or less than or equal to, or greater than or equal to. Okay, it just won't have the y equals that. It'll be one of our inequality forms. Step 2 then is to graph the boundary line. Now, one thing we need to know about the line is, in some cases, we can't be exactly on the line. If we have x has to be less than 4, x can't be exactly 4. Okay, we want everything below 4, but not including 4. So in this case, we would have to make a line that's dotted or dashed to say we're not including 4, but we're coming right up until 4 and doing everything that's below that. Okay, so again, we include the boundary line, or we fill it in as a solid line anytime we have the or equals to, less than or equal to, greater than or equal to. That's when it's going to be a solid line. We make it that dotted kind of dashed line every time it doesn't have that. So just the less than or the greater than. Okay, again, those ones saying we're not including this line, we're saying everything up until that point. The last step then, step 3, is we need to determine which region or which area we're going to shade by. And there's two ways to do this. Normally, if we have a line, if we look and we have a less than, or the less than or equal to, that means shade below that line. So everything less than that. Same thing if we have a greater than or the greater than or equal to, it means everything above that, or we just shade above the line. Another way to check these things are if we take a testing point. So we can plug a value in. So let's say I had like y is less than x minus 1. And I graphed that line out and I wanted to test the point 0, 0. Well, I would literally plug it in and say, is 0 less than 0 minus 1? Well, 0 minus 1 is the same as negative 1. So is 0 less than negative 1? No, it is not. So the area that 0, 0 is in, I wouldn't be shading. I'd have to shade the other area. And again, we'll go over this in some examples so we can see how it looks. Okay, let's look at our first example. Graphing the inequality y is less than or equal to 1/2 x minus 3. Okay, we need to first get it into the slope-intercept form, the y equals mx plus b form. Now in this case, that's already done for us. Okay, we can see our m, the slope, is going to be 1/2, and b, our y-intercept, is negative 3, or minus 3, down 3. So now we need to graph our line. So we'll take our y-intercept, this piece here. That means go down 3. So right here at 0, 3 is where we're going to start. Looking at our slope then, we know that we need to go up 1 over 2. Again, we always read from left to right. So as we start here, we're going to go up 1 and over 2 to this point. Moving left to right, up 1 over 2. Use the same up 1 over 2 from this point. We'll go up 1 over 2 to here. Up 1 over 2, and it gets us right here. Okay, so this is kind of the outline of what our line is going to look like. It's going to match up with these points. Okay, now again, we have to determine, are we going to use exactly on that line and do a solid line, or are we going to do a dashed line? Well, in this case, we have the or equals to, less than or equals to. So since it's less than or equal to, we do include everything on that line. So we make it a dark line, or should I say a solid line. Okay, it's not going to be dashed. We're saying we can include spots right on this line and they will work. Now we need to shade. Because we have y is less than 1/2 x minus 3, I need to shade everywhere below this line. So when I do that, it's going to look something like this. All of this area satisfies that inequality. And again, we can prove that. We can test it out. Let's go to the point 4, negative 4. So 1, 2, 3, 4, down 1, 2, 3, 4 would be this point right here, 4, negative 4. Now, that's in the shaded region, so what that means is this point should make our inequality true if we plug in these values for x and y. So let's check it out. Y is negative 4, less than or equal to 1/2 of x, which is 4, minus 3. Okay, so because it's in the shaded region, this should be true, this statement. So let's make sure it is true. Negative 4 is less than or equal to, well, half of 4, 1/2 times 4 is 2, still minus 3. This 2 minus 3 would be negative 1. Is negative 4 less than or equal to negative 1? Well, yes, it is. So because this is true, that's why this point over here is in the shaded region. In fact, everywhere there should be. Okay? I want to check one more point then to make sure our inequality is actually true. Let's check the point 0, 0. Notice how this point is outside of our shaded region. So this area should not be true. If I plug in 0, 0 into my inequality, it should actually not make sense or not be a true statement. So 0 is less than or equal to 1/2 x, which is actually 0, minus 3. We're trying to show that this isn't true. Again, we want it to not be true because over here, it's on the outside of our shaded region. Well, 1/2 of 0, 1/2 times 0 is still 0, so we'd have 0 is less than or equal to 0 minus 3. 0 minus 3 is just simply -3. We can change that piece. Now, is 0 actually less than -3? No, it is not. Because this is not true, that means the point that we picked, this point right here, should not be shaded. And in fact, it isn't. We have it in the not shaded region, which means that our inequality, or at least the way that we've graphed it, is correct. Okay, all of this area, all of the shaded green area, and including the blue line, would make this inequality true. So let's try another one. We need to graph the inequality y is greater than x. Okay, so the first step is always to get it into our y equals mx plus b form. And again, it's kind of already there. This is going to look like the equation y equals, oops, not equals 0, y equals x. So for y equals x, remember that's kind of like a hidden slope of 1 times x. And we can say plus 0 here because there's nothing behind it. So 0 is our y-intercept. So we start right here at 0, 0. And that hidden slope of 1 tells us go up 1 over 1, up 1 over 1, up 1 over 1, and so on as we're finding our points. So that's what our line is going to look like, somewhere along there. Now again, we need to ask, are we doing a solid line or a dashed line? Well, in this case, it is not equal to. Okay, so we can't include everything right on that line. So we have to make it a dashed line. So each of these spots, we should have a dash going through, because we're not including spots on this line, because we have to be less than that area. So we have our boundary line graphed. Now we need to shade it. Our inequality is saying y is greater than x. So we want the area above our line, which means I need to shade everywhere up here. So all of these points would work if we plug them into our inequality there. So let's check one of these points. Let's go right here, this spot, which is 1, 3. Okay, that is in our shaded area, so that should actually check out and make our inequality true. Okay, so y is 3 is greater than x is 1, and that's actually true. 3 is actually greater than 1. That's why this spot should be shaded. Okay, and you can check a million other points, anything you want, but again, it just has to show that it's not actually true. Again, looking at this dashed line though, we're saying that it's dashed because if we pick one of these points, let's pick this point right here. That's going to be the point 3, 3. If we plug that into our inequality, it would be saying 3 is greater than 3. And that's not true. 3 is not greater than 3. It's not bigger than itself. It's exactly equal to itself. So we can't include 3, 3 in our inequality, in our area that is true. That's why we have to have these dashed lines to show that it's everywhere near this line, but not touching this line, everywhere above it. Okay, that's what the dashed lines mean. Let's look at another example then. We need to graph the inequality 3x minus y is less than 4. Okay, like before, our first step is always to get these into the y equals mx plus b form. And for this one, we actually have to do a couple steps of work for that one, because it's not given to us as y equals mx plus b. So if we start with our 3x minus y is less than 4, from there, we need to move the 3x, this piece, over to this side. How do we do that? We would subtract 3x from both sides. When we subtract 3x from both sides, it gets rid of it here, and we're subtracting it on this side. So our new equation, or inequality, becomes negative y is less than negative 3x plus 4. From there, we have to get y positive. We want y all alone and we want it positive. So we have to either, two ways of thinking it, dividing by negative 1 or thinking of it as multiplying by negative 1. They both do the same thing. In either case, if we're dividing by negative 1 or multiplying by negative 1, all you're doing is changing the signs. All the positives become negative, all the negatives become positive. When we do that, also note, any time that you multiply or divide an inequality by a negative number, you have to flip the symbol, okay, that inequality symbol. So where it was before, y is less than, or should I say negative y is less than negative 3x plus 4, it flips and now it says y is greater than 3x minus 4. Now we have a y equals mx plus b form, so we're ready to graph. From there, like before, we look at our equation and say, where's my y-intercept? Well, that's at negative 4. So I start right here at negative 4. Using my slope, I go up 3 and over 1, up 3 over 1, up 3 over 1, and there would be some points. I need to decide, am I using a solid line or a dashed line? And in this case, because it is not equal to, the greater than or equal to, we'd have to use a dashed line. So I put my dashes in here to show that we have a dashed line. We cannot be right on this line. Now, am I shading everywhere above or everywhere below? Well, again, right here, this tells us greater than, we're shading everywhere below. I can take any point in this area, anywhere above this line, and it would make that inequality true. I'm not going to go through and check any more points because I think you kind of get the gist of it, but that's how you graph or solve these inequalities. Let's look at one more example then. 4x plus 3y is greater than or equal to negative 3. Like before, our first step is to get it into a y equals mx plus b form. So we have to start with our 4x plus 3y. First thing we need to do is move the x over to this side, or our x term, should I say. So we subtract 4x from both sides. That would leave us with 3y is greater than or equal to negative 4x minus 3. From there, we need to get y all alone, so we divide both sides by 3, and we'd have y is greater than or equal to negative 4/3 x minus 1. Again, we divided each of these terms, this over 3 and this over 3, and we got our final piece here, our final inequality. Now that we have our y equals mx plus b form, again, we can just say, well, our y-intercept is at negative 1, so we start right here. Our slope is negative, so we're going down. Reading from left to right, we need to be going down 4 and then over 3. So we'd go right here. Okay? Looking at these 2 points, this will make a line for us. And if we wanted to go in the other direction, again, from one point to another, it's still down 4 and then right 3. Or if you kind of go backwards, it would be saying go left 3 and then up 4. But this will still make a straight line. Again, we need to ask, are we doing a solid line or a dashed line? And in this case, because it has or equal to, it's going to be a solid line. So we start like that. Smartboard's getting a little off, that's fine. And that's going to be our solid line for this inequality. From there, the last thing to do is shade in the correct area. And because we have greater than or equal to, that means we're doing everything above that spot. So I'd have to do everywhere up here. This is my shaded region. And that's how you would graph inequalities.